Welcome to our discussion of the mean value theorem. We'll see that many of the results depend on one central fact, which is this mean value theorem. But in order to kind of get to the mean value theorem, we need to first look at Rolle's theorem. And Rolle's theorem says that if f is a function that satisfies the following three hypotheses: it's continuous on a closed interval, it's differentiable on an open interval, so that just means it doesn't have to be differentiable at the two endpoints, and somewhere in that interval f of a equals f of b. And in this case we're going to say the endpoints, right? So Rolle's theorem specifically says the function equals itself at the two endpoints. Then there is a number c in that interval ab such that the derivative equals 0 at that point. Now, before giving a proof, let's take a look at some examples. You can see very clearly that example A and B, right, f of A and f of B equal each other, and if we took the derivative of any point on that function, it would be 0 because it's the constant function. And then see how the rest, the endpoints, are all at the same height here and here, and here and here, and there, right? And somewhere in between we're getting these horizontal tangent lines. So Rolle's theorem seems very plausible from the pictures. We can prove that this equation, x cubed plus x minus 1 equals 0, has exactly one real root by using Rolle's theorem in conjunction with the intermediate theorem. The intermediate value theorem, remember, tells us that a function has to have at least one root if it's a continuous function on that interval and the two endpoints are opposite sides. One's positive and one's negative. So we take this function and we check, and f of 0 equals negative 1 and f of 1 equals 1. So we went from a negative to a positive. So somewhere between 0 and 1, we know that because this function is continuous, and it's a polynomial, so we know it's continuous, the intermediate value theorem tells us that there has to be at least one number c such that the function crosses that x-axis, right, and has a y value of 0. So we found one root. Now we want to prove that there's only one, that there can't be two. Well, that's where Rolle's theorem comes in. Because if we can contradict Rolle's theorem, then we know it's not true, and then we know we don't have a second root. So let's suppose that the function actually does have two roots. So that means there's an f of a and an f of b that equals 0. And because f is a polynomial, it's differentiable on the entire interval a to b, and it's continuous on the closed interval a to b, so it satisfies all of the conditions of Rolle's theorem. And by Rolle's theorem, there must be a number c in between those numbers a and b such that the derivative equals 0. But if we take the function and we take its derivative, which is 3x squared plus 1. If you don't remember what the function was, right, it was x cubed plus x minus 1. Take that derivative, that's 3x squared plus 1. So now we have the derivative 3x squared plus 1. Well, according to Rolle's theorem, there must be a number c on our interval between a and b such that the derivative equals 0. But that derivative never equals 0 because 3x squared plus 1 is always greater than or equal to 1. Because x squared is always greater than or equal to 0. The smallest it's ever going to be is 0, which means the smallest the derivative is ever going to be is 3 times 0, which is 0, 0 plus 1, which is 1. So the derivative never equals 0, thus we have a contradiction. And because we have that contradiction, that means the assumptions we made, i.e. that there were actually two roots, must be false, because if there were two roots, the function would satisfy all of the conditions it needs for Rolle's theorem, and then Rolle's theorem tells us the derivative equals 0 at some point, but because we know it never equals 0, right, there's got to be a problem, and so it's got to be the initial condition that f of a equals f of b somewhere, and therefore we've shown that there's only one real root. Now, the main use of Rolle's theorem is kind of giving us a launching point where we can get to the mean value theorem. And the mean value theorem is widely used. Much more than Rolle's theorem. Rolle's theorem is kind of just the stepping stone that gets us to the mean value theorem. So let's say f is a function that satisfies the following hypotheses, and you'll notice they're very similar, right? It's continuous on a closed interval, a, b, and it's differentiable on an open interval, a, b, and you're going, okay, those are the same two that we had for Rolle's theorem. Yep. Next, then there is a number c in that interval such that the derivative at that point c is equal to f of b minus f of a all over b minus a, or equivalently blah blah blah, all that stuff. Don't get bogged down by the letters. What is this saying? Okay, well, first of all, f prime of c, that's the derivative at c. That's just saying the slope of the tangent line. Okay, so the left-hand side is just saying the slope of the tangent line is going to equal something. Well, what is that something? F of b minus f of a, that's just a change in y's, right? That's y1 minus y2. And then b minus a, that's x1 minus x2. Holy mackerel, that's just slope, right? That's change in y over change in x over the interval a to b, right? You'll notice that we're using a and b. So it just says that on the left-hand side we have the slope of the tangent line. On the right-hand side we just have the slope of the secant line, the line that connects the points a and b. That's it. A and b and then f, right? So a and f of a and b and f of b. So this just says that the slope of the tangent line must equal the slope of the secant line, which is a pretty powerful thing. If you look at some pictures, you can see how it's kind of obvious, kind of intuitive. So there's our slope, right, of the secant line going from A to B. Connect those two dots, and then there's the point where the tangent line is the same. A to B, right, there's the slope of the secant line, and here we have two examples. So you'll notice that it doesn't guarantee us exactly one, it guarantees us at least one. So there can be more than one time where you'll find the tangent line equaling the secant line. In fact, if you have a constant function, it equals it everywhere, doesn't it? Okay, the slope of the secant line AB is just this thing that we were given. So as we've already talked about, the mean value theorem is just saying that there has to exist at least one point P where the tangent line is parallel to the secant line. Or in other words, there has to be at least one point on the interval where the instantaneous rate of change of the function is equal to the average rate of change over the entire interval for that function. And this is kind of logical if you consider, traveling in your car. If you average a speed of 60 miles per hour over a 4-hour trip, then there must have been at least some point in that time interval where your acceleration, your instantaneous rate of change, was equal to 60, right? You can't average 60 if you didn't at least get up to 60 at some point and stay there. And then because you were less than 60 at some point, then most likely you had to be greater than 60 at some point as well to average out 60. But you get the idea. Those two have to match. Alright, to illustrate the mean value theorem with a specific function, let's consider a very easy, simple function, x cubed minus x, and our interval is going to be from 0 to 2. So that's going to be our a and our b. So that's going to be our a and our b. Since f is a polynomial, we know it's continuous and it's differentiable for all x on its interval. Therefore, it satisfies all the things that we need for the mean value theorem. And thus the mean value theorem tells us there has to be a number c in that interval, so somewhere between 0 and 2, such that f of 2 minus f of 0, right, so the change in y's, has to equal the slope times the change in x's. This was just the other way we wrote the mean value theorem. And this might look familiar to you because this is just the point slope form, right? Y minus y1 equals m times x minus x1. That's all this really is. Just remember it comes from the idea that the derivative, right, so which is your slope, is just equal to change in y over change in x for your function, right, which is your f of b minus f of a all over b minus a. We can now plug in everything that we know. We know f of 2 equals 6, we know f of 0 equals 0, and we know the derivative is 3x squared minus 1. So we plug all that stuff in. We get f of 2 minus f of 0, right, our change in y's, that's 6, equals the tangent, 3 c squared. It's just now saying instead of the generic tangent, it's a tangent at a specific point, and we're just trying to figure out what that point is, right? So the slope of the tangent line times our change in our x's, which is 2 minus 0 is 2. We go ahead and distribute. We get the 6c squared minus 2, and then that's still equal to 6, right? You add 2 to both sides, 8, divide by 6, that's where you get 4/3. So now c squared is equal to 4/3. Take the square root, c is equal to plus or minus 2 root 3, but because the mean value theorem tells us that c must be in the interval 0 to 2, the -1 doesn't work, and we know that therefore c has to equal 2 over radical 3. And we just found the point where the instantaneous rate of change equals the average rate of change. Here it is in the graph. Another example, suppose that we have a function that f of 0 equals -3, and we know that the derivative of the function is always less than or equal to 5. So the instantaneous rate of change is never bigger than 5. The question could be, how large can f of 2 possibly get? So if we're given that the function is differentiable and therefore continuous everywhere, then we know we can apply the mean value theorem on this interval 0 to 2. And we only have to think about 0 to 2 because we only are concerned with what's happening at 2, right? So that's why we cut the interval at 2. Because we can use the mean value theorem, we know that there has to be a number c such that the change in y's is equal to the derivative at c times the change in x's. Once again, plug in everything that we know and solve for what we don't know. We've got f of 2 minus f of 0 equals all that other stuff, but we don't know f of 2, so that's why we're going to isolate f of 2. We're going to add the f of 0 to the other side. Where did the 2 times f prime of c come from? Well, that's very easily. That's your 2 minus 0. Okay, f of 0, remember, was -3, so that's where that comes from. And now we have that f of 2 is just equal to this. Well, we're given that the derivative is less than or equal to 5, so 2 times it, right, is always going to be less than or equal to 10. So we can sub that in and say that f of 2 always has to be less than or equal to -3 plus 10, which equals 7, and that tells us the maximum value for f of 2 is going to be 7. You might be thinking, who the heck cares? There actually are applications for this where you want to know what's the maximum value a function can take on a certain interval. Think about if your function was a cost function. You would definitely want to know what your maximum cost could be over that interval. Okay, some interesting facts come out of the mean value theorem. The first one is that if the derivative equals 0 for all x on an interval a to b, then the function must be a constant function, which makes sense, right? The only way to get the derivative equaling 0 everywhere, the slope of the tangent line to be 0 everywhere, is if you have a function that's just a horizontal line. And then we can expand that and say the only way that the derivative of one function, f prime of x, right, is going to equal the derivative of a different function, g prime of x, for all x's on your interval, is if the two functions are the same except for a constant, right? So f minus g is a constant. That's what this means, that the two functions are basically the same except for plus a constant. So f of x has to equal g of x plus a constant. That's the only way, because again, what happens when we just add a constant to a function, right? If we had this function g and then we add a constant to it, doesn't that just shift it up vertically? So that means if we took that constant away, it would look like f, right? It's just been shifted up. So those two functions are going to be mirror images of them, but just one's going to be shifted up or down if it's a negative number c. And so anywhere along the curve of f, you're going to have the same slope along the curve of g, and therefore their derivatives are going to be the same everywhere. Lastly, let's look at an example that highlights that we need to be careful when we're trying to apply Theorem 5. we have this kind of piecewise function, right? X over the absolute value of x. And we can see that it's constant on its two pieces of its domain, but it's not the same on those two pieces. Well, the domain of this function is everything except for 0. It's not defined at 0 because you can't divide by 0. And the derivative equals 0 for all x's in the domain. But the function is obviously not the constant function. Well, you'll remember that when we're using these ideas, it's built on the idea that these functions are differentiable everywhere, they're continuous everywhere, those types of things, right? So this doesn't really contradict theorem D because D is not an interval. It has a gap, right? It's got a hole in it. It goes from negative infinity to 0 and then stops and then goes from 0 up to infinity. And you'll notice that the function is constant on each of those smaller intervals. So if you took that function and just defined it for just one interval or the other, then theorem 5 would in fact work. So, the details do matter, that you have to have it defined over an entire interval. Alright, that's everything we need to worry about for the mean value theorem.